Okay, welcome back to this session on the Hammett equation. And now we're going to be looking at the plot of the rate constant versus the sigma, which is the raw value. And what scientists have seen is that in some situations, uh, if you're going to be plotting the rate constant versus the sigma, sometimes you've got a case whereby, like in this case, you've got probably a substituent like the methoxy group, the value is there, and maybe the methyl, what do you call it, maybe amino group, and then hydrogen, maybe it comes here. And then as you start having strong electron withdrawing groups what? Like cyanide, carboxylic acid, and maybe what? Even nitro group, then the plot starts to uh, the gradient changes and it starts to increase. In the other case is that you've got a case whereby uh, the plot is increasing. It means uh, as you have electron donating groups, there's a small rate, but as you're going to have maybe up to hydrogen, the rate increases maximum, and then as you continue uh, putting the electron withdrawing groups, then suddenly the plot, then the rate starts to decrease. Yeah. Now the scientists were looking at this equation. Just say, oh, I think we've now reached a dead end. We've got plots which you cannot be able to do what you cannot be able to explain. Now, now this is something very important for you who will be doing research. That when you'll be analyzing experimental data, and then you get a graph plot or certain observations which you cannot explain, please do not try to make the data agree with what you want, as opposed to trying to see how you can interpret those results. So maybe they would have just said, hey, we are only going to get up to here, and then the rest you're going to discard. What it is was to try to try to understand what was happening. So in the first case, the one which is down is called concave downward. You know, a concave, like a concave lens, yeah? Yeah. There is a concave and convex, yeah? So there is the concave downwards, and then there is the concave upwards, yeah? Concave upwards, concave downwards, yeah? Yeah. So let's look at the first example for the concave downwards. So in this case, they are looking at the study of the rate constant, a change of the rate constant, where you have, in this case, you are looking at the hydrolysis of either the methyl or the ethyl esters in very, very strong uh, sulfuric acid, which is 99.5 sulfuric acid. It means it's like what? We used to have a word for it. It was called oleum, yeah? Very, very strong sulfuric acid. So what was observed is that when you have methyl ester, the plot does not change even as you change the groups from the electron donating to the electron withdrawing. The plot is still having a unified straight line curve. What does that tell you? That when the rho is negative, it means that there is a developing positive charge in the reaction center, and therefore the groups which will be donating electrons, like the ones with the negative sigma values, are going to have the highest rate, and then the groups which are going to be withdrawing electrons, like the nitro group, are going to have the smallest rate, yeah, because they are destabilizing the developing positive charge, yeah. That's what you'd expect. Like for the methyl group, it tells you the uh, the plot is just single. But then what was observed is that when you have the like the one for the ethyl group, then as you're going to be changing the substituent from the from the strongest electron with withdrawing group to mild electron withdrawing groups, the rate was going down, which is what we'd expect for developing positive charge. Yeah, this the developing positive charge, and therefore the rho is negative. And then after some time, uh, it becomes zero, and then it starts to increase. Yeah, so that when you're going to have strong electron withdrawing groups, yeah, when you have what strong electron withdrawing groups, then now the rate starts to increase again. Now, what scientists have seen, the implication of this is that, especially for this one which is going down and then suddenly going up, is an indication of a change in reaction mechanism. The mechanism changes because in this case, you've got a case whereby the transition state, there's a developing negative charge in the transition state. Uh, so that any group which will be doing what will be withdrawing electrons are going to have a lower rate. So therefore, you not expect the groups which will be increasing positive charge to be doing what? To be having an increased rate unless the mechanism has changed to now have a way in which uh, the reaction center will now be receiving electrons. So this is an indication of a change in reaction mechanism. It's a change in reaction mechanism. So let us see how the change in the reaction mechanism is going to enable us to understand what is going on here. Let us take the example of the methyl ester. Can you be able to see well? Yeah. So there's the aromatic ring where you've got the X attached at either the para or at the meta position. So the first step is the protonation of that oxygen attached to the methyl group. So what has been seen is that the rate determining step is the is the is the falling off of the alcohol, methyl alcohol, to give the psyllium ion. Eh? To give the what? The psyllium ion. And in that rate determining step, look what is happening. The electrons are, this is the reaction center. The electrons are going out of the reaction center. Are doing what? They are going out. If they are going out, then electron withdrawing groups are going to destabilize the developing positive charge, which in this case is for their psyllium ion. Yeah, like the nitro group, cyanide, and carboxylic acid, as they are going to be attached to the R group, to the RL group, they are going to do what? They're going to destabilize. I think let me put this one as not as R but AR. Yeah, RL group. Yeah. Good. Okay, so they are going to destabilize the positive charge. So that's why you are going to see, as you are going to be plotting for the methyl group, the more the positive the sigma value, the lower the rate. Yeah, that's what we'd expect. Now the interesting comes when you're going to be plotting like the one for the ethyl ester and probably the propyl and the rest. Yeah, so this is what's going to be happening. Yeah, in the initial stage, up to probably where the substituent is probably the unsubstituted RL group, like in this case is hydrogen, the plot will be similar to the one for the methyl ester. It means if you've got CH2, CH3, this is the first step, and this is what's going to be happening. So this means that that the electrons are going to be going away from the reaction center, and you're forming the psyllium ion. You're forming what? you're forming the acylium ion. But what has been observed is that as you're going to be increasing the sigma value to have more electron withdrawing groups, what has been seen is that at extreme those electron withdrawing groups like the cyanide and the nitro group, what's been happening is that after a certain position, the mechanism does not create the acylium ion, but but under strong electron withdrawing groups, uh, the alkyl substituent like the ethyl, propyl, butyl, and the rest are going to be stable enough to fall off, so that it's going to be stabilized in the reaction mixture, and then that uh, ethyl or propyl or maybe butyl carbocation picks up water in solution to be able uh, to form the alcohol. Yeah. So the methyl group will give a very unstable carbocation. But the more the alkyl groups, the more stable the carbocation. So it means that when you're going to be having something like the ethyl group, then you're going to be generating carbocations, which are going to be stable in very strong sulfuric acid. Like it. So uh, so that in this case, from this point here, the mechanism changes from the rate determining state changes from the formation of the acylium ion, whereby the electrons are going out, and then after this point, this is the mechanism in which you are generating a stable carbocation, which whereby the RL group, even if you're going to have strong electron withdrawing groups like the cyanide and the nitro group, because the electrons are going towards the reaction center, the electron withdrawing groups are going to stabilize that carbocation more than the one which are not going to be stable. So that you're going to see that the increase in the plot after a certain point, it means that electron withdrawing groups are going to stabilize the reaction center. So the concave down is an indication of change in reaction mechanism. It's an indication of change in reaction mechanism. Okay? So so let me stop there, and then you're going to look at the case for the concave upwards and what it tells us about the reaction. Okay? I hope you're enjoying, yeah?